Welcome to this session on AES algorithm. In this session, we will approach the subject as any casual student would, whose interest is in using AES and not much in its intimidating mathematical logic. We intend to cover the logical and mathematical context of AES in another video to be released shortly. Our approach is to learn by practicing. We therefore recommend that you download AES keys and AES 128 ENCR DECR XLSX from the link given in the description. Those Excel workbooks use regular formulae that are available in MS Excel and not any macros. Please also download nist.fips.197.pdf from csrc.nist.gov/publication/fips listed under number 197. Our Excel book uses the sample case given in the appendices A and C of that PDF. It would therefore become much easy for you to follow our workings and also validate the results with those given in the document. We feel that some understanding of DES algorithm would be of much help. If interested, you might consider viewing our 5-part DES algorithm videos. On account of its 56-bit key size and increasing computing power, single DES is considered to be a security risk. AES algorithm was announced on November 26, 2001. Though the popularity of AES is rising by the day, the triple DES version of DES is still being used in banking circles. Mind you, triple DES has not still been broken into. Kerckhoffs's principle: security of a cryptographic object should depend only on the secrecy of the private key. It should not depend on the secrecy of the algorithm itself. AES is a published methodology proposed by Belgian cryptologists Vincent Riemann and John Dayman, from whose surnames the word Ringdale is derived. Approved by National Institute of Standards and Technology (NIST), a metrology laboratory and a non-regulatory agency of the United States Department of Commerce. So, the working of AES is fully known to everyone, like the DES methodology itself, and the encrypting key is the only secret part. While both are symmetric key encryption algorithms, major differences between them are as follows. Key size: we supply 64-bit key to DES. It is then reduced to 56 bits, and from this 16 subkeys are derived, each of which are further reduced to 48 bits. Ringdale has three key sizes: 128, 192 and 256 bits, from which 44 or 52 or 60 subkeys having length each of 32 bits are derived respectively. Plain text is 64-bit in DES and 128 bits in AES. Substitution tables: the logic behind the contents of 8-number S tables of DES was never revealed. AES has a single S table and its contents are fully validated using mathematical theory. DES is a bit level operation, while for most parts AES is byte level operation. This takes us into the finite field of Galois fields. Both are iterative block ciphers. DES iterates 16 rounds, 48 rounds for triple DES. AES undergoes 10 or 12 or 14 rounds depending upon the key sizes of 128 or 192 or 256 bits. You may pause the video to read the contents. Key expansion: there are two parts to any encryption methodology: the key expansion part, the encryption decryption part. We will now consider key expansion part in this video and will use AES keys.xlsx workbook for this session. Please refer to Appendix A on page 27 of FIPS.197.pdf that you have downloaded. Enter the 16-byte cipher key given there in hex form in cells B4 to Q4 in summary sheet of the workbook. You may ignore the plain text given in the workbook. This is not relevant for this session. The keys for 192 and 256 bits are given in pages 28 and 30. But to begin with, we will concentrate on 128-bit key expansion. The key contains 4 words W0 to W3. This key gets rearranged under cell range F09 to J12 in the same sheet, 1 word per column. Note the placement of bytes. Cell B4 goes to F9, B5 goes to F10, not to G9, and so on. Therefore, while filling this block, always follow this order. This key set forms one block. Similar procedure for 192 and the 256 bit keys. For 128 bits, MK equal to 4. For 192 bit key, it would be 6 words, MK equal to 6. And for 256 bit key, NK equal to 8. NK equal to key length divided by 32. This block contains the initial cipher key. For encrypting the plain text using 128-bit key, we have to iterate over 10 rounds. Refer to this table. Also, before beginning the encryption, we have to XOR the initial key with the plain text block. So, other than the initial block, we need a total number of 10 more rounds. So, our total number of rounds go up to 11 and we need 44 keywords. Therefore, in the below key expansion activity, we will be expanding the initial 4-word key to 40 more words. XOR implementation in our workbook. In cryptology, XOR operation is used extensively. In MS Excel, XOR operation is available only from 2013 version. So, for finding XOR of a hex using earlier versions of Excel, we needed to write a macro which we wanted to avoid. If you have the latest version of MS Excel, then you may consider substituting XOR in place of VLOOKUP wherever they occur inside the formula. So, we have computed XOR values for hexadecimal occurring in the range of 00 to FF and tabulated the results in cell ranges M3 to N65538 as a VLOOKUP table. The way it is implemented here is to concatenate the two hexadecimals and look for their XOR result. Thus, 011F under column M means we are trying to XOR 01 with 1F and place the result 1E in column N. Each round of key expansion involves 4 activities. Root word. The function root word takes the last word of the input block W3 now with A0, A1, A2, A3 as input, performs the cyclic permutation and returns the word A1, A2, A3 and A0. In the key sheet, note cell value E4 has moved to cell F3 and so on, and the value in topmost cell E3 has moved down to cell F6. This completes the rotation activity. We do this root word for every round. 2. Subword. Subword is a substitution function that takes a byte and substitutes the value from the S box. The S box is similar to the one that we saw in DES algorithm, but the difference is that in DES we had 8 S boxes. Here in AES it's a single S box that services all substitution requirements. We look up the substitution value of cell F4 in the lookup table given under data sheet of the workbook in the cell range A3 to C258 under E and C column and place it in cell G4. The DCR column would be used during decryption. Rcon is the round constant. The round constant word array Rcon I contains the values given by x power I minus 1 0 0 0 0 0 0 with x I minus 1 being the powers of x in the field Galois field 2 power 8. Also I starts at 1 and not 0. So x power 0 equal to 1, the round constant is 0 1 and this appears in the cell range h3 to h7. For the second round 2 power 2 minus 1 equal to 0 2 and so on. These are not just algebraic values but modulo 11b values. More on this on the separate video. For the 8th round, Rcon equal to 80. But for the 9th round, it is 2 power 9 minus 1 and not equal to hex 100 but 1b. This is because of the modulo 11b operation. The values are available in the data sheet. We do a lookup for getting the appropriate round constants. The addition of round constant is for the purpose of destroying any symmetries that may have been introduced by the other steps in the key expansion algorithm. Please keep in mind Rcon is different from round key. They are not to be confused with each other. This round constant in column H is XORed with subword in column G and written in column I. Note that it is the first byte that is changed and the values of the rest remain unchanged. Generate round keys. Word W0 in column B is XORed with column I and written in column J. That is, when we write fourth column, our NK is 0, 4 minus 4 is 0. So we find the 0th column value and XOR. For W1 in column C is XORed with column J and written with column K. Word W2 in column D is XORed with column K and written in column L. Word W3 in column E is XORed with column L and written in column M. This completes one round of key expansion. This is followed by 9 more rounds. We have 44 words in all. Cell range B9 to F2 in key sheet is nothing but rearrangement of the keys placed one below the other or used in the encryption rounds. The key expansion algorithm ensures that AES has no weak keys. A weak key is a key that reduces the security of the cipher in a predictable manner. For example, DES is known to have weak keys. Weak keys of DES are those that produce identical round keys for each of the 16 rounds. You would have noticed that in 128-bit key, it is one-to-one correspondence with the rounds. However, that is no longer the case with, say, the 192 or 256-bit key, which we'll explain presently. The 192-bit and 256-bit AES key expansion differs only on the following counts. The rot word, subword, Rcon and XOR operations are done at the end of every NK columns. This is 6th column for 192 and 8th column for 256. Since our NB continues to remain 4 on account of the block size remaining same, we extract round keys at the end of every 4th round. The expansion is continued until 12 round keys are extracted for 192 and 14 for 256-bit key. We are going to use the round keys in the same order while encrypting and in the reverse order while decrypting. Here are the workings. Here NK is 6, 0 to 5. We do the rot word, subword, Rcon, XOR. But while extracting our NB equal to 4, the first 4 goes as round 0, and the remaining number these two, they go here, and these two go here. Okay, 2 rounds over, and whatever is remaining, these 4 go as the third round key, and again these 4 go as the fourth round key, and so on until we come to 12 rounds here. In 256 is the same thing. Here nk equal to 8, 0 to 7. So we extract the first 4 as the first round key and the next 4 as the next round key. And this is the third round key, and this is fourth round key, and so on until we extract all the 14 rounds. You will also find that the round constants are stop with 80, that is 8th round constant, and here it stops with the 5th round 540. When the key size is expanding, you are going to extract more round keys per key, so round constant will naturally get reduced. So from 8 keys you are going to get 2 round keys in 256 bit, and in 192 with 6 keys, 1.5 round keys per key bit, per 192 bit you are going to get. That's the reason here it is going to get reduced. The round argon is going to get reduced as you work with longer key bits, longer key bits. But why are they given then? In the data sheet you will find, if you are going to stop with this, why are they given here? That is because if the plain text is also going to increase from 128 to 192 or 256, there will be a need for these things. But for some reason, it was not adopted, and so we are also not using. We recommend that you check or start generating different keys, and these values can be validated with whatever is given here. You may now experiment with various keys to get a firm grip on the AES key expansion logic. Thank you. We'll meet again in AES 128-bit encryption decryption session next. Bye until then.